some function with I, J, K, right? I'll write it several different ways. Right, I think I've seen that before.
Yeah.
A single dot above means the same thing as that. We often use the single dot when we're talking about motion with respect to time. This is specifically a derivative with respect to time. Sometimes you might even just see R dot. Yeah, they actually usually just write R dot. This is the same as dr dt. At this point, it's less important. In Unit 4, it becomes very important. It's with respect to time. There are other ways to differentiate these vectors to do things differently and cleverly. At this point, we're doing it with respect to time. Leave some space. There are some more. Actually, I need space for the position as well. Acceleration is the same as velocity, v dot, dv, dt, but it's also therefore the same as r dash dashed, or r dot dot, or d squared dt squared. Different ways of writing the same derivative. You will see all of them, you need to be comfortable with all of them. Give a moment for you all to catch up. We can also go the other way, of course. If I have acceleration, then velocity is the integral of acceleration with respect to time. And position is the integral of velocity with respect to time. It's just the opposite of differentiation.
You know how you can write a double dash to imply the
second derivative, yes.
Can you do that for integral?
It's a little ambiguous. You can, you want me to go integral, double integral of acceleration dt, dt. You can, but we usually don't. Because it runs into, well, one of the issues is you've got a constant coming out of this one. You have to remember to put into this next one. So we just usually don't. There are other things, there are other kinds of integral symbols. There are circle integrals and line integrals, and it gets very complicated. We're sticking to simple. Let me give you some real examples to show you how this works. I have one example before that. Yeah, we may as well do it. A particle moves so that its position vector is given by t I hat plus t minus 2 squared j hat. T is greater than or equal to 0. This was only two-dimensional. How boring. You do have to be able to do this with 3 dimensions. Except maybe not here. Because here we've got equation of motion of a particle travelling in a straight line. Now in physics you learn some formulas. Not allowed to use those formulas. In specialist maths they've been very clear. You have to work this stuff out using calculus every time. Always use calculus. Don't use V equals U plus AT. Always use calculus. One of the main reasons you have to do that is because you have to use it with constant, like in physics, but also non-constant acceleration. So it's going to be complicated. Stay with us, Julia.
I'm just thinking about it.
Okay. Non-constant acceleration. You'll see in a moment. I think this one's only going to have constant acceleration. And then the next thing we have to do is 2 dimensions. We have to do motion of plane, projectile and circular motion. This one is none of those things. This one's actually a parabola. No. It's interesting. Okay. No, it is a parabola. Okay. I want you to find me velocity. I want you to find me velocity at time 1 and velocity at time 2. And I want you to sketch the path and draw the velocity vectors at. Sketch the path and these 2 velocity vectors. Do you want time to have a go or do you want me to do it with you?
Just do it like behind us a little bit.
Okay. Oops. Velocity is r dot. Differentiate. You can use the chain rule for the j hat component or you can expand the brackets, your choice. Did you use the chain rule?
Yeah.
Okay. Doesn't make any difference. Can I go on yet, Julia?
Yeah.
Okay. Is it that simple?
That's where I go. Wait.
Oh, no, 2 minus 2, correct. That makes more sense. I like that better. No.
Is this tick active?
You don't need a calculator for this.
Part C.
What?
For part C.
You can sketch this.
Yeah, but it's just easier. Put it in, just copy and you're finished.
You're still going to have to work out where the point is at time 1 and time 2.
Yeah, that's easy though.
Okay.
I did that.
It's a problem. Sure. Good luck. This is the turning point form anyway.
Yeah. I'm a bit rusty with that one.
Y equals x minus 2 all squared. You need a calculator for that.
Just checking my answer.
Sorry?
Just checking my answer.
Sketch path.
That should actually be longer. goes 1 across and 2 down.
Oh, that's right.
Makes sense, Ben?
So,
I don't have to draw these vectors starting there, but I may as well. It shows where the particle is, which way it's going.
What do your brackets say?
V of 1, V of 2, 1, 1, 2, 0.
That's 2. Looks like 30 from here. Okay.
It was a bit messy. 2, is that better?
Yeah, thank you.
Describe the relationship between the velocity vector and the path of the particle. Can you describe the relationship between the velocity vector at any time and the path of the particle?
The gradient.
Okay, gradient, and it's related to that. The velocity is always tangent to the curve. The velocity is always pointing in the direction the particle is moving at that instant, which is always going to be along the curve and therefore at a tangent.
But how do you know if the arrow is downwards or upwards? Alright, sure.
And here, no J component, straight across.
If that was like 2i, it would be the same, right?
2i, well, it would be twice as long, but same direction. Yeah. In physics, have you done circular motion yet? So if I take an object and I swing it on the end of a string, and the string suddenly snaps, what happens to that thing that's swinging around? Which way does it go?
The point where it snapped would go in the direction that it snapped.
So this way?
Wait, which direction were you just spinning it? Yeah,
Snaps when it's here.
I'm going that way.
along the tangent.
Along the tangent, because that's its velocity at the time. Does that help? Velocity is always at a tangent to the path. Always. But think about these 2 points for me. Was here going that way? Was here going that way? Between those 2 points, which direction was acceleration?
Yeah.
It's got to turn this into that, so it's got to push this way. So the direction of acceleration is often not along the path.
So is it decelerating going that way?
It's complicated. It is actually slowing down. Yes, its speed here is root 5, and its speed here is 1. So it has slowed down. But when we're talking about 2-dimensional and 3-dimensional vectors, deceleration can be ambiguous.
Okay.
So it's accelerating, but not in the direction of movement, or necessarily against it either. In this case, acceleration is this kind of direction. Okay, D. Acceleration, please. What's the acceleration?
Two.
2? No. It's not 2.
It is 2.
No, it's 2j hat.
2j hat.
That's a vector. What you said was a scalar.
I meant 2j hat.
No, it's not what you said, is it?
No.
Be careful. Vectors and scalars are different. So in fact, its acceleration in this case is directly upwards. Directly upwards is its acceleration.
So that's not possible on a parabola.
That's exactly what's happening on the parabola.
How can it be straight up on a parabola and there's no point that goes straight up?
What's the shape of the path of that? A parabola, and which way is acceleration?
That way. That way.
Straight down. Which way is gravity pulling? Straight down. It's a parabola.
But what about straight up? When you throw it up? Does it go straight up?
No matter what I do, it's moving in a parabola. Ignoring air resistance.
But isn't the acceleration
Straight down, always straight down. Which way? What forces are acting when it's in the air? If I ignore air resistance, what forces are acting?
Gravity.
Anything else?
Air resistance.
With
You said
ignoring air resistance. So which direction is it accelerating?
that way.
Whichever way gravity is pulling.
So that way.
Only straight down. But what's going on? It already has horizontal motion. Newton's first law says unless there's a force acting horizontally, it's going to keep moving at a constant speed horizontally.
But if you check it up, isn't its acceleration like going this way and then this way or no?
While it's in the air. As soon as it's left my hands, the only force acting is gravity. Let me get something other than
But until it's to its vertex, like isn't it still?
At the vertex, tell me what's happening at the vertex.
It stops.
I'm surprised you haven't done this in physics, right?
We have.
What's happening at the vertex?
It stops.
Its motion stops. Is it accelerating?
Yeah.
Has the acceleration changed?
No.
Right? Acceleration is constant and downwards. Constant and downwards. Acceleration does not change, no matter what the object is moving like. Acceleration is always down, constant. Constant acceleration. Ask. I'd rather get this right in your head because it's going to help here and physics.
You know how the tangent describes the
Uh-huh.
velocity for the acceleration? The tangent will never be directly up, so how would you know if it's j hat? Like if it's 2j hat, that means it's going directly up.
Uh-huh.
Can you show that on the graph where 2j hat would be? And in what world would it look like?
Acceleration is always directly upwards.
Oh, okay, right. I'm imagining velocity rather than
Yes,
acceleration.
yes. That's what I'm saying. Let's get this straight now.
Okay, cool.
Acceleration is always upwards at 2. This gives us projectile motion. For the last dot point in topic 3 up there is projectile and circular motion. Projectile motion,
That's an interesting projectile path.
okay, it's inverted projectile motion, but it's if I flip that, it's the same thing as projectile motion, right? Acceleration is always constant for projectile motion. Not true for circular motion. You haven't done circular motion yet.
No, we have.
Oh, you have?
Doesn't look like it, does it?
You have done circular motion? So what can you tell me about the relationship between velocity and acceleration for circular motion? Not enough. Okay. Let's leave that for the moment.